Hello, Georgi Romanic here. Today we are going to test the accuracy of barometric equation. We derived this equation in my last video, so I highly suggest you check that video to properly understand what we are going to talk about today. In particular, we will use barometric formula or barometric equation to calculate the height above the surface where the pressure is half the value of the surface pressure. You will see how easy it is. We just need barometric formula and few assumptions. Before I do that, I would like to tell you that every time you derive some equation or you learn new concept in physics or atmospheric sciences, you should always put it to test and you should try to solve some particular problems to get familiar, as Richard Feynman would say, to get physical feeling for these things and these processes. And this is what we are going to do today. We will use barometric formula to solve a particular problem. To solve this problem, we start with hypsometric equation, or rather barometric formula that we derived last time, that P2 is P1 E G Z1 minus Z2 divided by RT average. Where, remember, if this is the surface of the Earth, this was the height Z1, and in our case Z1 is equal to 0, and this would be height Z2 that we actually want to find in this problem. T average is the average temperature in this layer between Z1 and Z2. R is ideal gas constant for dry air, and value is equal to approximately 287 joule per Kelvin per kilogram. And of course, G is 9.81 meters per second square. To solve this problem, we have to introduce some value of T average between Z1 and Z2. And here I will just assume that T average is minus 5 degrees Celsius, which is 268 kelvins. Okay, the problem tells us that at height Z2, pressure is 50% of the pressure at height Z1. Well, that means that pressure P2 at height Z2 is P1 half, 50% of P1. Well, I will substitute this over here and I will get P1 over 2 is equal P1 E to G. Now Z1 is 0, so I will get only minus Z2 divided RT average. P1 and P1 can be cancelled, and from here I get, if I run with logarithmic function through this equation, that ln of 1/2 is equal minus G Z2 over RT average. Or from here we get that Z2 is equal R T average divided by G ln of 2. So I remove this minus, but I reversed order of logarithm. And this is now equal to R is 287. I will omit units because everything is in SI units. T average is 268 kelvins divided by G 9.81, and times logarithm of 2 is 0.693 approximately. So if you take a calculator, you plug in these values, you will get that Z2 is equal 5435 meters. So altitude where pressure is half of the surface pressure is about 5.5 kilometers above the surface. I would like to just at least qualitatively show to you how accurate this barometric formula is. I'm shooting this video during the month of March 2021, and the average surface pressure in Montreal, where I live, is around 1000 millibars or hectopascals to 1010 hectopascals. Which means that 50% of that value is 500 hectopascals. So let me just write it down. If P1 is around 1000 hectopascals, that means that P2 is around 500 hectopascals. And this formula is telling us that this 500 hectopascals should be around at the height of 5.5 kilometers above the surface. Now here I printed for you the mean height of 500 hectopascal isobaric surface for the entire month of March 2021. The colors are the anomaly in respect to the 1981-2010 base period. So we are not currently interested in colors. These lines, curved lines, are what we are interested. Just one more note that the values here that I hope you can see are given actually in decameters. So to each of these values we have to add 0 to get meters. So here you see 576, 598, oops, you cannot see. Here 598 and so on. Now this map represents the Northern Hemisphere. I took it from Climate Prediction Center of NOAA, and I'll put a link in the description so you can go there and check it by your own. This is azimuthal projection of the Northern Hemisphere, namely here is North Pole, the outer rim is equator, and here you see North America. Somewhere here I would say is Montreal, somewhere here, doesn't matter. And look, value here, so the mean value for the March 2021, the mean value of the height of 500 hectopascals is 540, and we need to add one more 0 because this is in decameters. So 5400, and look, our theoretical calculation is 5435. This just demonstrates how accurate barometric equation is, even with the assumptions that we incorporated here, namely there are no vertical accelerations and the air is perfectly dry. In the next video I will use barometric formula to explain how density of air changes with height. Until then, goodbye.